The inverse mapping theorem states the following. We take two Banach spaces x and y and a function f going from x to y. Assume that f is of class Cp in the neighborhood of a given point u0, and that the differential of f at u0 is a bijection. Conclusion is that f is the local Cp diffeomorphism near u0. So how do we prove this? So the first thing we're going to assume is that without loss of generality, u0 is equal to 0 and f of u0 is equal to 0. If not, just translate the function both in x and y space. Okay, and now the goal is to prove that f is a bijection from a small ball around the origin into another small ball around the origin, this bijection, and that this bijection has smooth inverse, as smooth as the data allows. In other words, what we want to prove is to solve the equation uniquely, f of u is equal to f, for f in BR and u in B epsilon. Okay, so what do we know? We know that u is rather small and that f is differentiable at the origin. So we might as well apply a Taylor expansion at the origin. So we have that f of u is f of 0, which is equal to 0 by assumption, plus differential of f at 0 times u, plus a small o of the norm of u. So really the equation we're trying to solve, which I call star right away, is equivalent to asking that df of 0 times u is equal to leading order f. Well, if I do this, of course, I forgot a correction term, which is small o of u. But since it's small, I put it to the right-hand side. I use the second assumption that df of 0 is a bijection, so I can invert this and rewrite it as u equal to the inverse of df of 0 applied to f minus small o of u. And who is this small o of u, by the way? Well, let's look. It's just the difference of f of u minus differential of f of 0 computed against u. Okay, so now you see the equation is really equivalent to finding a fixed point for the function which I just called capital G. And we have a tool to prove that a function has a unique fixed point. It's called the contractive mapping theorem. So we need to check that G maps some small ball, some closed ball B epsilon bar into itself is contractive. So we need to prove that. If we do this, then we're done proving that f is a bijection from B epsilon to BR, where R is going to be fixed right away. So let's see. We first need to prove that G maps B epsilon onto itself. So we need to estimate for u in that ball the norm of G of u. Let's go back to its definition, rather the first definition, and we see that G of u is going to be less than the norm of the inverse of df of 0 times the norm of f plus the norm of a small o of u. Okay, let me start with this second quantity. This quantity is small o of u, so I can make it very small if I want. I can make it less than epsilon over 2 times this constant, let me call it k, if epsilon is small. So that's the very definition of a small o. And this whole quantity, let me call it r. And let me assume also that f is in the ball of radius r. So this whole thing is also less than r. So you see epsilon over 2k plus epsilon over 2k times k, the whole thing is bounded above by epsilon, and we've checked that G maps B epsilon into itself. It remains to prove the contraction property of G. So let's take u and v in the ball, and let us estimate norm of G of u minus norm of G of v. So now let me look at the second line right here. This is bounded above by the norm of the inverse mapping of df of 0. And then I have f of v minus f of u minus differential at the origin v minus u coming in from the difference of these quantities at v and u. Okay, so let's try to estimate this last thing. This is the quantity that we already called k, and let me call this vector e. So we have that e by the fundamental theorem of calculus, which is equal to the integral from 0 to 1 of d by dt of f of u plus t times v minus u dt. So this is the first piece, minus differential of f at the origin times v minus u. And now by the chain rule, it's easy to compute this quantity. And it's going to be equal to what? The differential of f computed at this intermediate point, u plus t times v minus u. The whole thing applied to v minus u, which is also a common factor here. So I might as well factor it out, even put it out of the integral since it does not depend on t. And we are left with this expression. Now look more carefully at the integrand. U is in the ball of size epsilon, v as well, so this point also is in the ball of size epsilon. So this means this point is very close to the origin, and since f is assumed to be c1, the norm of this whole quantity can be made as small as I want. And I can make the norm of this, if I want, to be less than 1 over 2 times k. So bingo, you plug that back into here, and you get that in the end, this g of u minus g of v is less than 1/2 the norm of u minus v. So we've just proved that f from b epsilon to br is a bijection, and it remains to prove that the inverse mapping of f is indeed a smooth function, as smooth as the data allows. So we're going to take an element of br in y, and let's take an increment which is also in br. Okay, and now we're going to let u be the unique solution of f of u is equal to f. Okay, and we can do the same thing with f plus k and call u plus h the corresponding solution. Okay, so we have a vector k, which is going to be a small increment. So first thing we should check is how big h is compared to k. And the claim is that the norm of h is controlled by a constant times the norm of k. So how do we see this? Well, we can do again a Taylor expansion of f, but this time as u at the point u, and say that f of u plus h is f of u plus the differential of f at u computed at the point h plus a small o of the norm of h. And this quantity is what we called k. And actually, no, I'm sorry. This was equal to f plus k. That's right here. So we have f plus k and f here. If I subtract one to the other, I just get k, which is equal to df of u times h plus a small o of norm of h. And now I do the same trick as earlier. Really, what I have is to leading order, h should be equal to the inverse of f of u computed at k. But it's not exactly equal to this. We have that h is the inverse of df of u computed at k minus this small o of norm of h. By the way, our original assumption was that df was invertible at the origin, but since it's also c1, we know that for u small, df of u is also invertible, so what I wrote is correct. So from this, we conclude that the norm of h is bounded above by the norm of the inverse of df of u times the norm of k plus the norm of the small o. And again, this is a small o, so if I take h very small, I can guarantee that this times this is less than 1/2 of h. So I can make this less than df of u inverse times k plus 1/2 of h. And this 1/2 of h, I can reabsorb it into the left-hand side and get my claim that h is controlled in norm by the norm of k. Okay, we're almost done now, so now we can compute the increment f inverse of f plus k minus f inverse of f. By definition of u and u plus h, this is exactly equal to, look here, u plus h minus u, so it's simply equal to h. And what is h? We wrote it here, is the same thing as the inverse of df of u applied to k minus small o of norm of h. So in other words, this whole thing is equal to df of u inverse times k. And then this whole thing is a small o of norm of h, but since h is controlled by k, it's also a small o of norm of k. So what we have proved is that f inverse is differentiable at f, and the differential of f inverse at f is equal to what? The differential of f at u inverted. So if we reread this equation functionally, what really wrote is that the differential of f inverse is the composition of the differential of f with the inverse mapping of f inverted. And you see now the smoothness property up to Cp is going to come out of this equation by a bootstrap argument, which I leave for you to do.